Hello and welcome to today's class. Today we'll be looking at tensile testing. We'll review what a simple tensile test looks like and what a simple stress strain curve which has been produced from a tensile test, what that looks like. So in order to understand our material properties and so that we can compare them easily, one simple test that we can do is a simple tensile test. So we would take a specimen, circular cross section, would look something like this. Sometimes people refer to this as a dog bone specimen. Circular cross section, necking in the middle. This center section would be our gauge length. It says constant cross section, so that would be our gauge length there. Gauge length. And that would have a known cross section. Let's call that area A. And we apply a load. Let's call our load P. So we can measure the stress. Stress is force over area. We've got force, we've got our area, and our we can also then measure strain. Strain would be change in length over the gauge length. So change in length over original length. And then what we can plot is stress against strain. And a typical stress strain curve for a low carbon steel would look something like this. So if we were to plot stress against strain, initially our material would be elastic, and then we'd see this plastic deformation, which would look something like this. So initially, it's obeying Hooke's law between 0 and let's call this point A up here. Okay, Hooke's law. F equals Kx. K is the stiffness of the material. It's the gradient of this line. And the gradient of that line is the Young's modulus. Young's modulus is stress over strain. dy stress sigma by dx strain. So this is dy by dx. It's the gradient of that line. It's the Young's modulus of the material. It's when the material is behaving elastically up until point A, this straight line on this curve here. Now, beyond A, there is a small region where the part is still elastic, in that if you remove the load, you would go back down this line to 0 strain, so there'd be 0 permanent deformation, but the line is no longer straight beyond A. It's no longer obeying Hooke's law. Point A is called our limit of proportionality. Point B is called our elastic limit. Now, for all intents and purposes, assume A and B are the same. They're so close to each other, we can assume that they are the same. So we assume A and B are coincident. Beyond B, we've then got permanent deformation. And what I mean by that is, if we get to a certain point on this curve and then we remove our load, we would go down in a straight line, parallel to this point here, actually. We'd go down in a straight line. So let's say we got to this point here, we remove our load, we'd go down in this straight line here, parallel to the original line, and you can see we have some permanent strain, some permanent deformation. So that's how much we would have strained our material. So beyond B, we've got plastic deformation, permanent deformation, permanent set. Now, beyond B, our curve increases here to point C, and point C is known as our upper yield point. It's as far as our material goes along this curve here. We then see a drop in stress to this point here. Let's call this point D. Point D is known as our lower yield point. Now, beyond point D, for relatively small increases in stress, we see very large increases in strain. And how much strain we see is a measure of the material's ductility. So a very ductile material would have a very long drawn out section here, and very a material which is not ductile and very low ductility would not have a long drawn out section here. Beyond D, we get up to our maximum stress. Let's call this point E, and that's known as our ultimate tensile stress. So we're applying our load, we've gone past our linear region to our non-linear region. Our stress is increasing, and when we get to point E, we're seeing a combination of elastic and plastic deformation. Beyond E, up until failure, point F, we're starting to see this area here, neck. We're seeing a reduction in our cross-sectional area as our part necks, and then eventually it would fail at point F. So between D and E, it's known as elastic plastic. Beyond E, we're seeing plastic deformation as our part starts to neck. Point E, like I say, that's known as our ultimate tensile stress. And in order to get that, we would get the stress at that point there and divide by the original area. And that gives us a measure of the material's ability to carry load. So that's what our typical stress strain curve would look like. So as we apply our load, our part starts to deform elastically and then plastically. And like I say, at point E, then we start to see necking, and actually the cross-sectional area would increase. So actually what we're measuring here is not true stress strain. It's called nominal stress or engineering stress, because we're using the original cross-sectional area in order to work out the stress. Stress is force over area. We're using that area. And actually, when the part starts to neck, that area reduces. So actually, the true stress is going to increase. We take the true cross-sectional area. So what we're looking at here is nominal stress against strain, or engineering stress against strain. True stress against strain curve would actually look slightly different. Let's find a clean sheet of paper. So if we were to plot stress against strain, if we were to plot stress against strain, our nominal stress strain curve, the one that we've just drawn, looks something like this. Okay, so that is nominal. Stress. definition of our nominal stress would be our force divided by that original area, that cross-sectional area of our dog bone prior to it being loaded. Actually, our true stress strain curve would look slightly different. The elastic bit would still be the same, but as soon as we start to see some plastic deformation, our true stress strain curve deviates. And once we get past the ultimate tensile stress, it massively increases. Okay, so this would be our true stress. Like I say, once we've gone past this point here, our ultimate tensile stress, we're seeing significant necking. So the true stress is going to significantly increase. Stress is force over area. And actually our force might not be increasing at this point, but our area is reducing. So therefore the stress is increasing. So our true stress equals our force divided by our actual cross-section, not actual area. In most cases, we use the nominal stress strain curve. So most stress strain curves that you will see will be showing you the nominal stress or the engineering stress strain curve. But actually, just be aware the true stress strain curve does deviate from that because of this necking that we're seeing in our specimen. Now, what we've shown so far is a stress strain curve for a low carbon steel. And we see this behavior here. We see an upper yield point and a lower yield point. Now, for high carbon steels or for non-ferrous metals, actually we don't see that behavior there. So we need to think of another way of measuring or comparing those materials. So if we were to plot stress against strain, the elastic part is still the same. Then rather than the upper and lower yield point, we simply see this behavior. Okay, so we need to consider there's no definite upper yield point or lower yield point. So we use something called the proof stress. Proof stress. And that is the stress at which point, if the load is removed, we see a certain amount of permanent deformation. So we're loading our specimen, we're going up past, or up this region here, up this elastic region here, we start to see plastic deformation. And then let's say we got to this point here and we removed our load, our part would move, down this line here. This line here would be parallel to that original line. And we get to this point down here where we're seeing zero stress, but we are still seeing some strain. We're seeing some permanent deformation. Strain. Now, if that was, I don't know, let's say 0.1% strain, what we've loaded there is we've loaded that material to a point where we are seeing 0.1% proof stress. So by doing that, by loading different materials to see the same amount of plastic strain, when we remove our load, we can compare those materials. So we've loaded this material until we're seeing 0.1% proof stress. So now we go up this curve here to this position here, and then we come straight down this line here, and we're seeing 0.1% strain. If we were to load it again, we would go up this, back up this line to the point where we were before, and then we'd carry on along this line. Let's say we got to this point. We got to that point, and then if we unloaded it, again, we'd come down parallel to that line, to that initial stress strain curve. So we'd come down here, back down to this point down here. Again, we've got zero stress. We're seeing an even greater amount of strain. If we were to load that again, we'd go back up this line to this point here, and then we'd carry on along our stress strain curve. Now, notice each time that we do that, we've got a higher stress. So we've got a stress there, which corresponds to 0.1% strain. And then when we carry on loading it, and then unloading it, and then loading it again, we get a slightly higher stress. Let's call that sigma 1, let's call that sigma 2. Okay, notice sigma 2 is greater than sigma 1. So we're seeing this elastic region, a higher stress before we start to see this plastic region. And then we unload, and again we see this elastic region. Again, the stress is even higher, the elastic region is even higher before we start to see this plastic region. And what we're seeing there is something called work hardening. By applying some work, we're raising the point at which we change from a linear region to a non-linear region. If we look back to our original stress strain curve that we drew, this one here, that's what a typical stress strain curve would look like. We've got this linear region, we've got this non-linear region. We've defined our upper yield point, our lower yield point, our ultimate tensile stress. We understand the idea of proof stress. We understand the idea of work hardening. We also understand how we would get our stress strain, our Young's modulus from our stress strain curve. And also we need to think about the fact that this is engineering stress strain that we're looking at here. Our true stress strain curve would head up here because we're seeing this area reducing. So therefore our stress is going to increase. If you've got any questions regarding any of that, just let me know. But those are key concepts which we're going to be using moving forward.